G'day there, you're watching the Aussie BIM Guru, and today I'm going to be covering how to assess shortest distances in 2D using Dynamo in Autodesk Revit. So I'd like to thank Sean Fruin from Sigma AEC Solutions for sharing a workflow on using a package called Topologic in order to assess the optimal duct layout parametrically, which also inspired me to make this video. So previously I've looked at using the space analysis package for Dynamo in order to find the shortest distance using what's called a space analysis lattice in order to assess the shortest path to reach another point. This was an interesting workflow. I do have a video on it you can watch if you're interested, but today I'm going to show you what's a more efficient method I've found. So instead of using the space analysis package, we'll look at something else. So the limitations for the space analysis package that this other option will overcome, one is the processing speed. This method is a lot faster, and there's the ability to actually set desirability of each part of the path that the person or the object is traveling on. So you can do like a street map, and you can say to avoid back streets, for example, or to try to avoid back streets, for example, using a dictionary with key values associated to each part of the path. So very powerful, and as well as that, you don't have just to do a 2D lattice using this package. You can use a 3D lattice as well, so very exciting. So the alternative approach is a package built by a group of people called Topologic. I've been talking to Dr. Wasim Yabi, not quite sure how to say it, sorry, and on LinkedIn, and they've been very helpful in figuring out how this package works. And I'm just using it for one use here. It's actually used for a lot more than just shortest route analysis. So you can find it at this website here, and essentially it looks at topology instead of geometry. So in Dynamo we have a list of things like solids, meshes, surfaces, polycurves, curves and points. The topology has an alternative approach for each one, and topology is a more holistic approach in that each element is made up of another set of topological elements. For example, a edge contains vertices. And a wire contains edges, a face contains wires. It keeps climbing in hierarchy. So it's an alternative approach that, I guess, simply put, it gives you much more control over the data structure of your geometry. It's hard to explain. I recommend reading the website. They describe it really well in this section below. Feel free to pause and read it if you want. But essentially, it just gives you more power and speed over dealing with geometry versus Dynamo's geometry limitations. So there's a hierarchy you can see here of how the topological data is ordered by class, and all the really intricate relationships that exist between all these classes of topology. So it's very interesting. But today we're just going to look at it for root analysis. It's important to note that Topologic is available for both Dynamo and Grasshopper. I haven't used it for Grasshopper yet, but I imagine it works in a very similar way. So it's great that they've sort of reached out to both platforms. So today's workflow is going to be looking at finding an optimal route through a network of lines. So essentially we're going to break up all the lines into pieces at their vertices and their intersection points, and then we're going to use the Topologic in order to find a route through this, the shortest route possible. It's important to note that you can do this in 3D as well. I have tried it in 3D. It is slower, but it can do it. And I'm not going to focus on it today because it's quite complicated. But this could have a lot of potential. You could do things like fire egress analysis in 3D through like a hospital, for example. All you have to do is convert all your data into topology, or into nodes, vertices, which you can turn into edges and wires in topology, for example. So definitely worth looking further into. But hopefully today, this will help show you a use for it. So we're going to be using a couple of custom nodes today. We're going to be using the intersect all for curves from Bimorph nodes in order to break all our curves into segments. We're also going to be looking at deconstruct polycurve and deconstruct point from Lunchbox in order to assess the components that make up our geometry at various points in the script. But what's most important is we're going to be using Topologic. So we're not just going to be using the shortest path analysis method. We're going to be using a lot of other nodes that relate to handling topology, or from geometry, or turning geometry into topology. So it's definitely worth keeping an eye as I go through. I'll point out when I'm using nodes from Topologic and when I'm not. I'll be using version 2.0.3 today. I believe that Topologic works in the new builds of Dynamo as well for 2020, from what I've seen. But I think probably a version 2 would make the most sense to use at least. So without further ado, I'm just going to jump into Revit. So I've got a bit of a sore throat still, so hopefully you can understand me. Alright, so what I'm going to do is just create a whole bunch of lines, and I'm just going to create like a little, almost like a pretend roadmap just a whole bunch of curves that intersect, and you can make them intersect in more complex manners. You can make little subpaths. You can make one that breaks off here, one that breaks off there. So that's essentially like our lattice, or our testing that we're going to run a shortest path through. So say if I start here and I try to get here, obviously it's going to be something a bit like that. So what we'll do now is just jump into Dynamo. And the first thing we need to do is actually select all our model elements. I'm just going to turn off automatic mode. So what I'll do is just do a select model elements. Come on. Oh, I'm in 3D view, that's why. So I'm going to select all of these curves. I'm going to go back into Revit, marquee them, and we'll get a whole bunch of model elements. You can obviously select these curves in many ways. You could actually select all lines of a particular type if you didn't want to keep selecting them each time you change your geometry. But what we're going to do with that is just get their geometry. So we'll get these lines for analysis. And then I'll just zoom out so that I can see my lines in Dynamo. And I'll just move those up a little bit out of the way. Okay, so what we need to do now is we need to actually break all of these curves into segments, because at the moment these are just whole curves. They don't break at each intersection that they make. So we're going to use a little bit of a complex method to find out how to do this. But what we're going to do first is we're just going to flatten these at the moment, because I believe that each of these will have a sublist. So we'll flatten this first, and I'm just going to turn off my previews as I go. What we're going to do with that is we're going to create a list. And the reason we're going to do that is because we're feeding this into an intersect all, which expects a list of elements to intersect. So now we have all the lines at the same level in a list. And what we'll do with this is we're going to get our intersect all curve method. And this is from the bimorph nodes package. And we're going to find all the intersections. We're also going to take our flattened curves beyond this point at a certain stage. So we'll need to move that to the side. What we have here is just all the intersection points as they occur between all these curves. So we have 14 intersections at the moment. I'm just going to flatten this list again. And I'll just turn off the preview, and there we go. Now we should have all of these points. Okay, so this is really like the first step of the script. We've just created all these intersections. What I might do is just group this and just call this intersect all. I'll just move this up to the top. What we need to do now is break all these curves by their intersections, which is the hard part. So what we're aiming for here is actually the curve split by points. But what we need to do is find out which points sit on which curves in order to split them by these respective points. So we're going to do a little bit of list mapping in order to do this. So I'm just going to get list map, because we're going to run a function across all of these lists. So we're going to be working across our list of all our curves. So for each curve, we want to find out if these points intersect. So we're going to say, do these points on these curves intersect? And we should get a list of lists, basically with a Boolean set per curve for which points actually intersect. We'll just move this off to the side. What we need to do now is run another list map. So it's getting more complicated because we need to apply this map across our points. So from our lists of Booleans, we're going to run a filter by Boolean mask on a mapping function. And what we want to do is filter a point list, and we're going to get the in, or the trues, of the Boolean list, which is being inserted at the mask level. So it's a little bit complicated, this step, but essentially what you end up with is a masked list of points. So basically per curve, these are the points that sit on that curve. So now we can split our curves by these points. So I'll just go back and get my curves. And for each curve, we'll split it by its respective list of points. And what we should end up with is a list of curves. So each of these essentially represents a piece of the curve. So we have 1, 2, 3, 4, 5, 1, 2. You can see we've basically broken our curves. This is a really handy method. I've used it quite a lot. in other workflows where I'm trying to break up curves by intersections. So definitely worth remembering this one for future reference. I'll just call this break curves. What we might do is just go back and turn off some of our previews again. So I'll turn off these. Really all we want is just our curves at the end. So we'll turn off our preview, and we just end up with all of these little curves. And I'll just deselect. Cool. Okay, so now we have all of our segments within our network. So now we can feed this into a topological study, which is great. What we're going to do first is we're going to get a start point and an end point. So we're still not quite at the topological point, apologies. What we're going to need to do is get a select model element. Well, we need two. We need one for a start point, one for an end point. What I'm going to use in this case is just a circle. And I'm just going to draw it pretty close to where I want to start and pretty close to where I want to finish. Cool. So we've got a start point and an end point. And I'll just go and set these. So we'll get our start and we'll get our end. And I'll just call these 1 and 2. And what we want to do with these is we also want to get their geometry. So I'll just copy a geometry node over from our initial geometry conversion. And what we'll get is circles at the moment. So we just want to get the center point of those circles. I'll just find it by looking for circle center point. And this will give us a point for where we're starting and where we're finishing. And at the moment, these don't sit on our network. So we need to find the closest point on the network to these particular points. So I'll just turn off my preview for these. So essentially these are our start and our end point. And what we're going to do now is find all the start and ends of the curves in our network. So we're going to get our start point of curve and our end point of curve. And for each curve from the start of our network, we're going to get the start and the end point. Okay, and then what we're going to do, create a list just to put them together. And we're going to flatten it as well. Just so we have a big list of points with all the starts and the ends. And we just want to find the closest one in each case. So I'll just turn off some of these previews because we'll get a lot of points otherwise. Whoops. Bear with me. Preview. All right, so what we'll do is we'll just call this all start end of curves. So of these 2 points, we want to find the closest point from this list. There's a few workflows you can use to do this. There's probably some that are more direct than the one I'm going to do, but this is just my preferred one because I find it quite quick to set up. So what I'm going to do, I'll just maximize my window again. We're going to get a distance to node. So distance from geometry to another. And we want to find out how far away this point is from each of these. So I'll set this to longest lacing so that it checks every single point. We should end up with a list of numbers for how far away each one of these is. So we can find from this the closest distance. We'll do the same for the other point. And then what we're going to do with these is we're going to sort them by a key. So we're going to go sort by key, or list sort by key. And we want to sort our start point, end point list by the distance that they are away from that point. And likewise, I'll do the same here. So in this case, I need to make my, whoops, that's my key, that's my list. And if I run this, you'll end up with a list where everything has been sorted. So all the points have been sorted based on the distance. So you can see here that now we can actually find the minimum distance and also the point that occurs at that minimum distance by going through the sorted list. I'm just going to make a code block and I'm just going to call on the list of start points, or the list for the start point and the list for the end point. And I'm just calling on index 0 in this case. So the first item in each list, which is the closest point. And then you can see we find the first and the last point in our desired path as it occurs on the endpoints of our curves. So we can continue with these 2 points as our start and our end vertex. So that's pretty much everything set up for the topological study. So now we get to the fun part. So thanks for bearing with me if you already got through that. We're going to go to the fun part now. So what we're going to do first is we're going to need to convert our geometry into topology. So what I'll do is I'll just get a topology by geometry. And you'll know that the topological nodes are up here because they have this little union box symbol. So we're going to get a topology by geometry. So this is a pretty flexible node. It knows how to convert a majority of Dynamo types, Dynamo geometry types into topology types. So what we're going to be feeding in here is curves. And the equivalent for curves in topology is edges. So you'll see now we end up with a whole bunch of little topologic edges as a result. What we might do is just flatten before we feed this in, just to get all the little segments at the same level. And I'll just turn off the preview for that. Great, so now we have a whole bunch of topologic edges. It's important to note you can't actually see topology in Dynamo Preview, so that can be a little bit hard. If you do ever want to see your topology, you just need to get a topology to geometry node, which works the other way around. So it creates geometry from topology, and that essentially takes topology and converts it back into the equivalent Dynamo type. I might just turn on my geometry scaling to extra large, because at the moment it's just giving me a warning because of that. Okay, and there you go. You can see this is how we can get our curves back from our topology. So it's a really easy system to work with. What I'm going to do is take my topology, and what I want to do is add a key to it. So I want to add the data about the length of each curve, because I'm finding the shortest distance, so I need to tell each curve how long it is. And then we're going to build a dictionary which the final shortest distance study can take advantage of. So I'm just going to get a dictionary by key values. And we just need, sorry, I need to do it the other way around. I'll just look it up. I think it's dictionary by key values. I've got a few custom packages that have dictionaries in them, so I probably need to just make sure I'm using the right one. My node browser is very slow these days. I think I just have too many packages. Come on, bear with me. Wow, it's really slow today. I think it will be one of the first ones if I look up diction. So it should be dictionary by keys and values. Not get dictionary key values. Somewhere here. By keys values. Here we go. So dictionary by keys values. Great, that's what we're looking for. So we're going to call our key length in this case. That's just the name of our key. And we're going to get the length of each curve before we convert it to topology. So I'm going to take each curve, run this, and we should get a number, which is the length of each curve or pathway on our network. What I need to do now is use a topology set dictionary, which is coming from the Topologic package. So we'll do set dictionary. It's important to note you can set multiple dictionaries. So there's a lot of power with dictionaries and topology. But I'm just going to take my topology and I'm going to attach my dictionary information. And what it will do is associate each length field with the topology. It's interesting to note that the topology actually stores the dictionary data inside the topology now. So this will actually carry that data with it as it goes, even though you don't see it. So a very interesting storage method by the package. The last thing we need to do now is we need to turn all our edges into a wire or a polycurve essentially. But it's better than a polycurve because it doesn't have to be one continuous connected loop. It can just be a whole set of curves. So we're going to get wire by edges. And again, this is from the topology package. So create a wire by a set of edges. And what it should do is convert all of our edges into a wire. It's also important to note that our dictionary carries through with the wire, which is really impressive. So I have no idea how they've done it. It's very, very cool, but it's carrying all the dictionary values with it. So I'll just create this one and say topology and dictionary creation. What we need to do now is actually go and set up what's called a topological graph, which allows us to assess the shortest distance of our paths within our wire. So the first thing I'm going to do is just get a graph by topology. Whoops, I'll just go by topology. And all we're going to do in this case is we're going to take our wire and we're going to graph it. And we'll just say that we are doing a direct study in this case. So we're using the centroid of our topologies. I won't go into too much detail about what a graph's methodology is, but essentially it's just the method by which we set up the ability to analyze our wire and its various segments. What we need to do now is find our vertex on our topology at coordinates, because we need to find our start point and our end point on our topology. So we're going to get vertices at coordinates. And from our graph, we need to find the x, the y, and the z of the point, and we'll set a tolerance for how close we can find a vertex. So we're just going to get the deconstruct point node from Lunchbox, and we're just going to go and get our start point and also our end point as well. So we're going to feed in x, y, and z. In this case, I won't set a tolerance. I'll just let it be the default of 0.0001 because we're pretty much on the point, so it should be able to find it. We're just going to get another one, and instead we're going to find the point on the topology for our end point. And what we should end up with is two topological vertices. Great, so we've got a vertex and we have a vertex. So we can use these in order to analyze our shortest distance. So I'll just create another group for this, just to sort our topological graph. I'll just call that create graph. And the last thing we need to do now before we assess our shortest distance is go shortest path. And we're going to get shortest path. It's important to note you can do shortest paths as well. You don't just have to do one single study. Very important. So what you can do here is take your graph, take the start vertex, take the end vertex, but it's important now that we need to call on the key from our dictionary for our edge key. So that's our length in this case. You can type in length here manually, but what I usually like to do is just go back and connect it to the dictionary name here. So it's just calling on the same value in all cases. What I'll do is just run my graph at this point and my study, and we should end up with a wire, so a point with a lot of curves. This is going to be our shortest distance. We can't see it right now. So what we need to do now is go topology geometry and convert our topology back to geometry. And this is very exciting because at this point we should just be able to see our shortest path. And there we go, you can see our shortest path highlighted there. So really quick, really flexible. What I might do is just override the geometry color before I show you some updates to the path, just to show you how flexible the script is. So I'm just going to go and find my curve split by points and turn off the preview for that. And what I'll also do is just get a geometry color node, and we'll just make our path like a light gray. So I'll just get color ARG by ARGB, feed it in, and let's just make it 125 for everything. So just a half transparent gray. So now we can see our network. What I'll do is just copy these nodes and go forward, and we can just make our path red in this case. So I'll just take my topology, and what we'll do instead is have 255 plus 0, and we'll just say that green and blue are 0, and red and alpha are 255. Turn off our geometry, and now we should see our path in red. What you can also do maybe is just translate or move the path just up a little bit so it's not sitting on top of the network. So I'll just do translate geometry by direction and distance. I'll translate in the Z direction, so I'll get a Z axis, and we'll just translate by 100. And instead we'll feed this in as our geometry, and now it should sit above and be a bit easier to see. So that's pretty much it. What we can do now is really just keep running topological studies. So we have our two start and end points nominated already, and we have all our curves nominated as well. So what we can do is just minimize Dynamo a little bit, and we'll just focus on our topology, or on our path, not our topology, our geometry in Dynamo, so we can see our path. Let's just move over and center it. And what I can do now is just start moving these around. So I can say, let's go from here to here, run, and look how quick that was. It was almost instantaneous. It figured out how to get there so fast compared to the shortest analysis package. Note that it didn't go around this corner here. It knew that it can save some distance by going this way. So it's interesting that it finds little savings in distance. But it's almost like, a little mini Google Maps in Dynamo. It's pretty powerful. And this is really just the starting point for your journey into Topologic. It's been an amazing package to start learning, and I can see so many uses for it already in what I'm doing, especially for space planning and egress analysis. So really a lot of commendation to the team, especially for making this free as well, just launching it out open source for everyone to use. Hats off to them, very impressed. Thanks for watching all the way through to this point. I know that it's been quite a long tutorial, so I appreciate you watching this far. But essentially that's all for today. So if you've got any feedback or comments, or you want to just have a better idea of how you might be able to use Topologic, feel free to either reach out to the team or just comment down below or get in touch with me, and I'm happy to talk to you further about it. If you're not already following and subscribing, feel free to do so. I make videos about 2 times a week, and I continue to do so for a very long time, hopefully. Thanks for watching today, and hopefully I'll see you in the next video. Thanks. Take care.